classification. What is a classification problem? Well, in a classification problem, typically, the goal is to understand why an observation belongs to a certain category, to a certain group. So the category can be just a 0 or 1 encoding, or it could be a category of education, or it could be urban versus rural. It can be any type of discrete value. And so our observation is encoded with a y variable that takes this discrete value. And there may be some other variables, x, that may explain why we observe our observation to belong to a particular category. That is, x may explain why we observe a y being 0 or 1, for example. And so, in classification, we will have tools named classifier. A classifier is a tool that provides a classification for a y variable using, or not, some additional information from other variables, the x. But as usual in machine learning, we have supervised versus unsupervised classification. In supervised classification, we observe the category for each observation. So one may learn and estimate the impact of other variables on that classification. This is, for example, what we do in logit regression that we will see later on. In unsupervised classification, on the other hand, we ignore the category, if it exists, of each observation. And we have to discover that. So the goal is to classify observation using all the variables that are here without having any information of what category means or how many categories are there. This is also called clustering. In this course, we will focus on supervised classification. So let's take an example. You observe households that are either in urban or rural areas, and one variable that is education. Sometimes in machine learning, the variables are called features, but we'll come back to that a little bit later. So here we observe education. This is encoded as a continuous variable. It's a level of education. It's an index of education that takes value from 0 to 1. And we will have some of the households that are in urban or rural area. On this graphic here, you have urban household in orange and rural in green. And so you see along the education line, you have households that belong to either one or the other category here. So a classifier here would determine which value of education separate rural from urban, where to put the cursor. The cursor definition will be the classifier. So typically there will be a threshold, and if x, that is here, education, exceeds that threshold, we will say it's urban. And if it's below, it's rural, of course. So from that simple example, we can construct maybe a more insightful example on a 2D example. So now you observe households that are either urban or rural, and two variables, education and income. So we have a 2D graph that looks like this. You have points everywhere, and you see that there on the education line, it seems that there are more orange, as well as on the income vertically, there are a little bit more orange. But here, once again, what a classifier can do on this example to separate the two populations of rural or urban households. Well, typically, a classifier will determine a boundary using both education and income to separate rural from urban. We'll see later on different types of boundary construction, but here we will focus on classical tools, classical classifiers. So from this graphic here, we may have, for example, a linear relationship between education and income or a nonlinear or whatever shape you can imagine, to separate and to have a rule that states how you can, from education and income, determine whether a household is rural or urban area. So here you have an example of linear classifier. You see that there is a line that separates the two population of household on this education income graphic. And so the separation rule is something like x prime beta exceeds some threshold with T0 is known, and this is the separation rule that will determine what is the value of T0. In our example, it could be just that the linear combination of education and income is greater than 2,0, then we will say that it's urban. How to construct this boundary, how to compute this classifier, we will see that later on, and you have all of that explained in a companion document that comes with this video. You will see example of many classifiers and as well as the code so for you to reproduce. But for the moment, let's us focus on some example of classifiers. So here you have a linear classifier, but there may be some nonlinear ones, such as the one I show you here, where here the separation is no more a linear combination of education and income. It has some shape of quadratic function there. So it's nonlinear in the variable education and income, and it's perfectly fine. You have your rule to separate that. Another example can be nonlinear in the other way. It has some weird shape here, and it works well as well. It's a little bit more complex maybe to understand the relationship between education and income there. There can be classifiers that provide very nonlinear decision boundaries and decision zones there and classification zone there. And it is hard to understand how the two classes are built using education and income. But maybe if the goal is really to predict from education and income in which of the two region, area or urban you are, maybe this one can be more accurate, more precise than the other. But in fact, what does it mean to be a better model, to be more precise, to be more fit to the problem you are facing? In short, how to select the right model? Well, we first have to have in mind what is the goal of that. The goal is to have the best classification, but what best means? We need a criterion to determine what is a good classifier. And for that, we may use measure of fit, and we will see that there are many of them and which are different and specific to different problems. In fact, there are a lot of them differing in their spirit, in their computation, and in their goal. We're going to see the most important one here, but of course there are many and all depend on the problem you're facing. The first one will be accuracy. How accurate is my classification? There is an important notion also that is based on the confusion matrix that we will see in a minute. There are two related measures that are called sensitivity and specificity. We will see that also later on. There are other stuff such as kappa, and we will discover that right now. But keep in mind that each criterion answers to a different question and put a focus on a very specific dimension of your definition of what is a good classifier. So maybe the most straightforward one is accuracy. Accuracy corresponds to the probability of being accurate, of being true. That is the probability that what you predict, the f hat of x0, remember that when we put a hat, it means prediction. So what I predict with my classifier f is exactly what I have observed. So y0 equals my prediction, and the probability of that corresponds to being accurate. If the probability is high, I am very accurate. If it's low, I'm not so accurate. We, of course, want the maximum possible accuracy. So computing this probability could be a good way of knowing whether our classifier is accurate or not. Equivalently, we may want to minimize the error rate or misclassification rate, which means the probability of not being in the right category with the classifier, not predicting well the category. For computing the accuracy as well as many other measures of fit for these classifiers, we will use the confusion matrix. The confusion matrix is a very important tool that allows us to measure how many predictions were accurate, were good. And since we have two outcomes in our example, either you predict urban or rural, and you can observe urban or rural as well, so we have four cases here that are named true positive, false negative, and true negative. These names are not so obvious. Just keep in mind that one category will be called positive, in our case urban, and the other will be called negative. So that's why you observe some positive or some negative outcome and you predict some positive or some negative outcome. And you can be true or false. I hope this helps you memorize this, but we will do some example here. What is the accuracy? Well, the accuracy from this table is just the ratio between the number of cases where you are right, that means the top left and the bottom right cells, the diagonal. On this, you were right, you predicted well. And you divide that by the total number of cases. So let's take an example on our sample that you have in the companion document. You have the number here. So we observe urban or rural, and we predict urban or rural using our classifier. So urban is a positive case here. So we have the true positive, that is 87, and the true negative, that is 69. These are the good predictions that correspond to the observation. The two other, 28 and 24, these two numbers correspond to false prediction, right? So we have a total of 208 observations, and here we have an accuracy of 0.75, which is, well, good, maybe, we don't know. It seems to be quite well. In 3/4 of the cases, we predict well. But maybe this is a little bit too limited, because accuracy is just one number from a complex situation, right? We have also this false prediction. And sometimes we are interested in correctly predicting a particular outcome. This is the case when the cost of being wrong differ. Imagine that being in urban area allows you to have some subsidy or something. If you predict well for an household, it's good, you can get the subsidy. If you predict it well, that's a big cost for him. So maybe you want to put a focus on that. And for that, we may need some other measure focused on a particular outcome. And this is what specificity and sensitivity appear here. And these numbers will come from the confusion matrix as well, but go in different directions, focus on different outcomes. So here is our confusion matrix again. Now I will focus on the first column, that is on the observed urban. And if I want to focus on this, what is called the positive case here, I want to know for how many of the observed urban I am correctly predicting. Here I will just focus on the first column, on the urban observation. And for that, I'm computing the sensitivity, that is my true positive over the total of what is observed as urban. And here I see that in 78% of the urban observation, I predicted well, which is good, but you see it's higher than the accuracy. I'm better on urban with my classifier. We have something that is similar to that, the specificity, but there will be also the called the true negative rate that focus on the other outcome, the negative outcome. Nothing pejorative here, it's just the name here. And we'll focus on the second column. And we will want to know on this population how many were well predicted. And you see, I predicted well in 69 cases over a total that is 69 over 28. So I predicted well in 71% of the case only. That's less than for the urban population. It means my classifier is better at predicting urban than predicting rural. This is an important feature of my classifier. Maybe that's important for me to select a classifier that is better on some direction. At least it's interesting to observe that. There is another problem. Sometimes we have imbalanced outcome. For example, imagine that instead of the sample we just seen, we observe that in 95% of the case we are observing urban population and only in 5% of the case rural. So imagine we only have 100 households and we have this here. Well, if you take a very stupid classifier that always predicts urban, that stupid classifier will have a very good accuracy. Why that? The accuracy is the diagonal. 95% of the time is good. See, it's predicting only urban, so nothing on rural. So 95% of the time is true because there are 95 observations in urban. And what about the sensitivity? Well, the sensitivity is even better because I'm only focusing on urban, and I'm urban, my stupid classifier is very good because it's always predicting that you are in urban situation. So when you have imbalanced outcome like that, maybe you will need another index to measure the fit, the accuracy, and the performance of your classifier. And for that, we will introduce the kappa index. The kappa index is defined to measure the accuracy when we have imbalanced classes. Its formal definition is given by this ratio where you have difference between the current classifier accuracy, the way we compute it, minus the accuracy of another classifier named PE here over this 1 minus PE. So the definition is a little bit complex, and once again, you have all the details in the companion there. Let's say just that the PE is the accuracy of a classifier that is uninformed, that is naive. It will operate purely by chance using no information. And with this kappa, you balance a little bit, you measure how well is your classifier compared to something that is more based on the real distribution of the two categories you observe. Anyway, this indicator is a little bit more complex, but will be very useful. What you have to recall is that the larger the kappa, as well as the larger the accuracy, or the larger the sensitivity, or the larger of the specificity, the better the model. So it's time for you to answer a few questions. I hope this question helps you to really understand this simple concept we have in classification, because we will use them for the rest of the course. To wrap up this sequence here, we have one important tool named the confusion matrix that gives you a comparison between what you observe and what you predict with your classifier. And if we want to know which classifier is good for a problem, or if a classifier is better than another one, we will need to compare confusion matrix, or we will need to compare accuracy, sensitivity, specificity, or maybe kappa to measure some important features of this classifier. Remember also that sensitivity is accuracy restrictive to the positive case, so-called positive, and the specificity is restricted to the so-called negative. And once again, these are pure formal definition of positive and negative. When the outcome is unbalanced, one may use a kappa as the better measure for accuracy. Which measure is the best depends on the context and on your goal. But we're going to see example in the next video.